In this presentation, I'll be explaining single phase half control rectifiers, or also called it is semi converter. Now let us see single phase half control bridge rectifier, or that's called the semi converter in continuous conduction mode. In this half control or semi converter, half control bridge rectifier, here two thyristors are replaced by two diodes. Here, of course, there are two method of connection, like one we call it as symmetrical configuration, other one we call it as asymmetrical configuration. Considering the symmetrical configuration, here you can see that fully controlled bridge, it was thyristors. Here these two things. Now that is replaced by two diodes like here. D1 and D2 are the diodes that is replacing corresponding thyristors. Therefore, two thyristors are replaced by two diodes, and here also another, this is called asymmetrical configuration. Here also two thyristors are replaced by two diodes. Then that operates only in one quadrant. In fully controlled bridge, as already we have seen the previous presentation, it can be operated either first quadrant or fourth quadrant. Two quadrant operation is possible. Either you can make voltage positive or negative, but always current is positive. Therefore, it can operate as either in first quadrant or fourth quadrant in the case of a fully controlled bridge rectifier. But in half controlled bridge rectifier, it can operate only in one quadrant, means that you can make only positive voltage as well as positive current. Or first quadrant operation is only possible in the case of, this half controlled bridge or semi converters. The configuration is, there are two types of configuration. One we call it a symmetrical configuration. Second one is called asymmetrical configuration. And the assumption is that load current is continuous and the ripple free, and average output voltage is never negative. We'll be deriving the equation for average output voltage, and you can see that it can never be negative, or it cannot operate in as an inverter. Therefore, it can only rectify that one, and it can be operated only in first quadrant mode. Now continuing the single phase half control bridge rectifier or semi converter in continuous conduction mode asset. Here we are considering there are two, as I previous slide I told here there are two type of configuration. One we call it a symmetrical configuration. In that one, here the thyristors are replaced by diodes here in each like 2 lakh cities. But in asymmetrical configuration, here the thyristors are replaced by two diodes. Now considering the symmetrical configuration, let us see that one. Here T1 during the positive half cycle, T1, of course D1, they are getting forward bias 0 to pi radians, and during the negative half cycle, T2 and D2 are forward bias. Now here at a finite angle alpha, the thyristor T1 is triggered because this is an uncontrolled device, switching device. Therefore, this is a controlled switching device because we have to fire the SCR. Therefore, we are firing the SCR at an angle alpha here. The T1 gets triggered, and then T1 and D1 will be conducting. Now, T1 and D1 will be conducting, and the path of this one is like this one, and the load is an RLE load. We are considering an RLE load, resistance, inductance, and a back EM, or say battery or source, DC source is there. Or this can be equivalent to a DC motor like back EMF, the armature inductance and armature resistance, like can be considered like that one. It's an RLE load in which when T1 is triggered, of course D1 is also forward bias in 0 to pi radians. Then the path is like this one from the source. Current is like this one, source current and T1, and then through the RLE load and returning back to D1, and this returning back. Therefore, that is the then voltage across the load, RLE load is same as the whatever the input voltage. Therefore, here you can say that from alpha to pi, once the current flowing through the diode for this SCR is here, you can see that one here. Once this goes to negative half cycle, this is not of course here T1 and D2 are conducting. Then during the negative half cycle, we can say that this is getting positive and this is getting negative, or in that case D2 is conducting. Of course D2 is forward biased. Therefore, from pi to 2 pi, if you see that one, the input voltage is negative. That the voltage at this point is negative with respect to this one, and that is why here we can see that one. Here T1 and D2 are conducting. T1 continues. T1 and D2 are conducting, or here the output voltage will become 0. Therefore, T1 and T2 are conducting, output voltage equal to 0. Therefore, at a firing angle pi plus alpha, here T2 is triggered, then T2 and D2 will be conducting, and again the current flow is like this one, and here the voltage at this point is the voltage at what same as this one. For here the voltage is positive with respect to this one. Again, then you will be getting the inverter voltage of this one will be getting at this point. Therefore, here output of this voltage will become same as the inverted version of this voltage at this point, or here you'll be getting this is the output voltage, and during that duration the thyristor T2 and the diode D2 are conducting. T2 and D2 are conducting. Again, during the positive half cycle from say here from 2 pi to alpha, you can say that from 2 pi to alpha here T2 and here we can say that T2 and D1 are conducting. T2 is still conducting because of the inductance everything. T2 is conducting, and the same time this is also getting forward bias. This diode is getting forward bias. Therefore, T2 and D1 are conducting. T2 and D1 are conducting. For that will be repeating. Therefore, the devices that are conducting different duration is that from alpha to pi, T1 and D1 are conducting. From pi to pi plus alpha, T1 and D2 are conducting. Therefore, output voltage is 0. And from pi plus alpha to 2 pi, T2 and D2 are conducting. From here 2 pi to 2 pi plus alpha, T2 and D1 are conducting, and output voltage is 0 during that period. Therefore, this is the output voltage for different instant, and what we are assuming is that load current is a constant. Load current is constant, capital I naught, and since the load current is constant, here you can say that one say when T1 and D1 are there conducting, the current is like this one. Therefore, the source current is in this direction. When T2 and D2 are conducting, this is of course the current comes here is a positive, current is coming to T2, and again load current is same direction, but here through D2, and here you can say that source current is opposite direction. That is why if you plot the source current, it is a rectangular. We can say that here it is equal to plus I naught, and during this period T1 D2 conducts. When T1 D2 conducts, we can get it is equal to 0, voltage across load equals 0. Therefore, the current equal to 0. That is why during period current equal to 0. Therefore, this is the waveform of the source current. That there will be a source current from alpha to pi, then again pi plus alpha to 2 pi. For that, this is the source current, and this is constant. Load current is assumed to be constant, and source current is like from alpha to pi, that is plus I naught. From pi plus alpha to 2 pi, it is equal to minus I naught. Now let us see the output voltage corresponding to this. What is the average voltage? That is, we have to find out the average value of this voltage, because we have to integrate this voltage from alpha to pi, and that it should be distributed over pi. For 1 by pi integral alpha to pi Vm sin omega t. This area is distributed, this area that is distributed from 0 to pi. And how much is that? Of course, that height we can say that's the normal method of calculating the average. For 1 by pi integral alpha to pi Vm sin omega t, or it is equal to, we substitute and we'll be getting it is equal to Vm by pi into 1 plus cos alpha. Therefore, the average voltage is equal to Vm by pi into 1 plus cos alpha. And if you analyze the source current you can see that one from alpha to pi it is plus I naught. From pi plus alpha to 2 pi it is equal to minus I naught. If you do the Fourier analysis of this one, different frequency components here, for that one you have to calculate the Fourier constant like A naught, An, Bn. Therefore, here if you calculate the Fourier analysis or do the Fourier analysis of the source current here, that is equal to, general equation is that A naught plus sigma n equal to 1 to infinity An cos n omega t plus Bn sin omega t, where the Fourier constants A naught, since it is a half wave symmetry is there here, because Ft equal to minus of Ft plus t by 2. That is called the half wave symmetry is there. If it is having a half wave symmetry, this waveform is having a half wave symmetry, then A naught equal to 0, that is half wave symmetry, and A1 equal to A1, that is like A1 equal to 4 by 2 pi integral alpha to pi I naught cos omega t into d omega t. It can be minus 2 I naught divided by pi sin alpha. Similarly, B1 equal to 4 by 2 pi integral alpha 2 pi I naught sin omega t d omega t, or 2 I naught by pi into 1 plus cos alpha. Therefore, we can get what is the, the fundamental components, Fourier constant corresponding to the fundamental, that is A1 and B1. A1 equal to minus 2 I naught divided by pi into sin alpha. I naught is this current, that is load current magnitude, and B1 equal to plus 2 I naught divided by pi into 1 plus cos alpha. Once we are getting A1 and B1, then you can calculate what is the maximum value of the fundamental, which is equal to square root of A1 square plus B1 square. So root of A1 square plus B square, if you calculate the square root of this, here A1 square plus B1 square, that is this, if you square plus square of this one, then you will be getting it is equal to 2 root 2 I naught divided by into root of 1 plus cos alpha, or again 1 plus cos alpha equal to 2 cos squared alpha by 2. If you substitute that one, you will be getting 4 I naught divided by pi into root of cos squared pi alpha by 2, or which is equal to 4 I naught by pi into cos alpha by 2. Therefore, 4 I naught divided by cos alpha by 2 is the, of course, the maximum value of the fundamental. Maximum value of the fundamental is this one. That is, if you take the fundamental of this source current, its maximum value is equal to 4 I naught divided by pi into cos alpha by 2. Of course, the RMS value is equal to the maximum value, because say sinusoidal one fundamental, that divided by root 2. 4 I naught divided by pi into cos alpha divided by root 2, or which you will be getting 2 root 2 I naught divided by pi into cos alpha by 2. Therefore, this is the RMS value of the source current. RMS value of the source current equal to 2 root 2 I naught divided by pi into cos alpha by 2. Thus, the RMS value of the fundamental source current IS1 is equal to 2 root 2 I naught divided by pi into cos alpha by 2. Again, we have calculated that fundamental, that is RMS value of the fundamental IS1 equal to 2 root 2 I naught divided by pi into cos alpha by 2. Now, the RMS value of the total source current, that is RMS value of the total source current, can be calculated. Again, root of mean 1 by pi into square of the current alpha to pi, Therefore, I naught square d omega t. It is the square of, then mean, take the root means square value, which is equal to, you take I naught into square root of pi minus alpha divided by pi. Therefore, this is the RMS value of the source current, and this is the RMS value of the fundamental source current IS1 as well as IS. Now, we have already defined the displacement power factor in the previous presentation. Displacement power factor equal to cos phi 1. Cos phi 1 is that cosine of the phase angle between fundamental voltage and fundamental current. Now, for that one, we have to derive what is phi 1. Phi 1 equal to tan inverse A1 by B1. Already we have derived the previous slide what is A1 and what is B1. Tan inverse A1 by B1 equal to the phase angle shift fundamental, that is phi 1, which is equal to tan inverse alpha, because here A1 by B1 you have to calculate. A1 equal to minus 2 I naught divided by pi into sin alpha. B1 equal to 2 I naught divided by pi into 1 plus cos alpha. A1 by B1 is calculated, and by doing the necessary substitutions we will get it is equal to minus tan alpha by 2. Therefore, A1 by B1 equal to minus tan alpha by 2, or tan inverse A1 by B1 equal to tan inverse minus tan alpha by 2, or it is equal to minus alpha by 2. Therefore, phi 1 equal to minus alpha by 2. Substituting here cos minus alpha by 2, it's equal to cos alpha by 2. Therefore, the displacement power factor equal to cos alpha by 2. Then distortion factor is the ratio of the IS1, fundamental RMS value divided by total RMS value, IS1 divided by IS. Therefore, IS1 is given here and IS is also here. And if you substitute here, we can get it is equal to, substituting this one, 2 root 2 divided by pi, square root of pi into pi minus alpha into cos alpha by 2. Therefore, this is the distortion factor of this waveform source current, and displacement power factor is given by cos alpha by 2. Then total harmonic distortion is given by, which is actually the RMS value of the harmonic divided by RMS value of the fundamental, or compared to fundamental or related to fundamental, how much is the harmonic, that represents total harmonic distortion. Square root of IS square minus IS1 square divided by S1. You substitute this IS1 and IS in this equation, then you will be getting it is equal to square root of pi into pi minus alpha divided by 4 into 1 plus cos alpha minus 1. Or total harmonic distortion also we have already derived in the previous presentation, it is equal to square root of 1 by distortion factor square minus 1. Therefore, here substituting this one, we can get it is equal to, that is this is the total harmonic distortion, and the input power factor is the product of displacement power factor and distortion factor. Therefore, it is the ratio of the active power, fundamental active power divided by the apparent power. Fundamental active power means it is equal to Vs into Is1 into cos phi 1 divided by Vs into Is, or Vs gets cancelled, or it is equal to Is1 by Is into cos phi 1, or Is1 by Is equal to, it is equal to distortion factor, and cos phi n is the displacement power factor. So the product of distortion factor and displacement power factor, that is the total power factor. That is, you are multiplying 2 root 2 divided by square root of pi into pi minus alpha into cos squared alpha by 2. Therefore, this is the total harmonic distortion of this waveform, the source current. Now let us see a few examples on this one. A single phase full wave semi-converter used to charge a 24 volt battery. Resistance is 5 ohm, that is connected in series with the battery to limit the current. A large inductor is connected for filtering. Find the output power, find the output power and input power factor for a alpha equal to 45 degree. RMS value of the input voltage is equal to 50 volt. Assume continuous conduction and ripple free current. Therefore, this is a circuit. It is a semi-converter in which these are the T1, T2. It is marked as T1, T2, and this is the RLE load. And we have seen this is the input voltage and this is the output voltage. And from alpha to pi, the voltage is same as this one. From pi plus alpha to 2 pi, it is the inverted version of this voltage. So this is the voltage that is available at the RLE load, across the RLE load. And we have derived previously what is the average value of this one. It is already derived. Therefore, the average value of the output voltage is equal to, this average value of this voltage equal to VDC equal to Vm by pi into 1 plus cos alpha. Alpha is given as 45 degree. Therefore, Vm you have to calculate. What is the Vm? Maximum value of the input voltage is given by RMS value of the voltage is given as 50 volts. If the maximum value equal to root 2 times Vm, or root 2 times 50, which is equal to 70.7, that much volt, 70.71 volts. That is the maximum value. And firing angle is given by 45 degree. Therefore, you can calculate the average voltage of this one, which is equal to Vm by pi, that is 70.71 divided by pi into 1 plus cos 45, it is equal to 38.42 volts. So the average value of this voltage equal to 38.42 volts. Then average value of the load current, you have to calculate what is the average value of the load current. This is the average value of the voltage, and the average value of the load current is given by, this is the voltage that is available here, that VDC minus this back or this voltage. Of course, there's a source, battery source is in DC motor, it is like a back EMF. Therefore, minus E divided by the resistance, that is the DC quantity, because this is a DC current, that is why it is equal to VDC minus E, only R comes, EDC minus E divided by R, because the current is constant here. Therefore, it is equal to 38.42 minus 24 divided by 5, battery voltage equal to 24 volt, that is minus 24 divided by 5, 2.88 amperes. Therefore, the load current equal to 2.88 amperes. Then output power can be calculated as VDC, already calculated 38.42 volts, and IDC, or the load current I0, which is equal to 2.88. Therefore, the output power equal to VDC into I0, which is equal to 110.65 watts. That is the output power. Next, the output power and input power factor, RMS value of the input voltage. You have to find out what is the RMS value. RMS value of the input voltage is given. Assume the continuous conduction. You calculated what is the output power. Then power applied to the battery. Therefore, this is the output power. The power supplied to the battery is equal to that is the battery voltage and the load current. That is, this much power is supplied. That is 24 into 2.8, 69.12 watts is the, that is, power given to the battery. And the RMS value of the source current. What is the RMS value of the source current? Because the source current is a, of course, it is a rectangular waveform. Now we have to find out what is the power factor at the input side. Power factor at the input side, and this is the source current. This is the source current, that is from alpha to pi it is equal to plus I naught. From pi plus alpha to 2 pi it is equal to minus I naught. For we have already derived in the previous slide what is the equation for the fundamental, RMS value of the fundamental of source voltage, source current, for source current. What is the fundamental? That is IS1. Similarly, what is the RMS value of the total source current? That is IS. Therefore, IS1 we have already derived the previous slide here. IS1 equal to I naught into root of pi minus alpha divided by pi, which is equal to I naught is derived as 2.88. 2.88 into square root of pi minus here alpha, that is 45 in radians, it is 0.785 divided by pi, it is equal to 2.49 amperes. Therefore, that is the RMS value of the fundamental source current. And similarly, the RMS value of this is the RMS value of the total source current, not the fundamental. It's actually the RMS value of the source current is this equation. It's equal to 2.49 RMS value of the source current. And RMS value of the fundamental source current IS1 equal to 2 root 2 divided by I naught divided by pi into cos alpha by 2. Or substituting here again I naught and cos alpha here, then you'll be getting 2.396 amperes. Therefore, the RMS value of the fundamental source current equal to 2.396 amperes, and the RMS value of the total source current equal to 2.49 amperes. And then you can calculate what is the input power factor, which is equal to the product of describe the displacement power factor and distortion factor. Distortion factor is given by IS1 divided by IS. That is IS1 divided by IS. IS1 divided by IS. IS1 means RMS value of the fundamental, and divided by the total RMS value 2.396 divided by 2.49, that into the displacement power factor. Displacement power factor equal to cos alpha by 2. Cos into alpha is a 45. Cos 45 divided by 2, or you'll be getting it is equal to 0.889. Now the power factor at the input side equal to 0.889. Now consider another example. A single phase full converter 1 kW power to a resistive load at alpha equal to 0. Find the firing angle for 0.5 kW output. Input voltage equal to 230 volt. Here it is where it's not a half semi converter. In this problem it is a full converter, or it is a full wave converter bridge circuit like T1, T2, T3, T4. And in that case the equation equal to we can here this is the fully controlled, and the solution is that Vm square root of Vm into sine here pure resistive load. So it is a purely resistive load, means that here we can see that one the voltage waveform is like that one, purely resistive, because there's no inductance as such. Therefore there's a discontinuity in the discontinuous conduction. Therefore here from alpha to pi T1 and T2 are conducting. From pi plus alpha to 2 pi here of course T3 and T4 are conducting. Therefore the output voltage, if you take the average value of the output voltage here you can calculate, which is equal to Vm by pi into 1 plus cos alpha, or 1 by pi integral alpha 2 pi Vm sin omega t, or Vm by pi into 1 plus cos alpha. Therefore the average voltage across the resistance for a full converter is given by Vm by pi into 1 plus cos alpha. And the problem it is given that when alpha equal to 0 degree, that is when alpha equal to 0 degree, corresponding VDC is given by Vm by pi into 1 plus cos 0, or Vm equal to RMS value 230, root 2 into 230 divided by pi into 2, or 207.07 is the average value that is across the resistor, 207.07 volts. And once you get the average voltage, the power is given by 1 kilowatt is across this. The power dissipated by the resistor equal to 1 kilowatt. Therefore 1000 watts. Therefore Vd square divided by R, that is the average value of the voltage square divided by the resistance, is the power dissipated by the resistor. For Vdc square divided by the load resistance RL equal to P. which is equal to 1000 watts. So for RL equal to 207.07 square divided by 1000, 42.88 ohms. Therefore, the resistance here is equal to 42.88 ohms. Now, the question is that find the firing angle for 0.5 kilowatt output. That is now 0.5 kilowatt, then you have to calculate what is the average voltage required. Therefore, RL is calculated, which is equal to 42.88. Then we have to calculate what is the voltage corresponding to this 0.5 kW. So for corresponding to 0.5 kW or 500 watts, what is the average voltage is given by, because as per this equation, we can say that VDC equal to P into RL. Then take the square root of P into RL. P is equal to now 500 watts into RL already calculated, or 146.42 volt is the average voltage required. Here the average voltage equal to 146.42. Again, the equation, you apply this equation, the average voltage is equal to Vm by pi into 1 plus cos alpha. 146.42 equal to Vm divided by pi into 1 plus cos alpha, which is equal to root 2 into 230 divided by pi into 1 plus cos alpha. From this equation, you can find out what is alpha. Cos alpha equal to 0.4141 and firing angle equal to 65.54 degrees. So for if you are making the alpha equal to 65.54 degree for this resistive load, the power dissipated here is equal to 500 watts or 0.5 kilowatt. Now let us see another example in which the example power supplied to a 230 volt 1 kilowatt resistive load is to be controlled. Here it is controlled by full converter as well as semi converter. Find the following quantities for both type of converter, for fully converter as well as semi converter. For a type of converter for a 500 watts output. Now average value, RMS value of the input current. What is the average value? What is the RMS value of the input current? What is the fundamental component of the input current? And what is the displacement power factor? What is the distortion factor? What is the total harmonic distortion? And what is the input power factor? All these parameters has to be calculated for both cases. One we are considering it is equal to a full converter, another one is equal to semi converter. Now let us see the first, it is equal to a full converter. Full converter means all will be thyristors T1, T2, T3, T4, and this is an RL load here, and the load resistance can be calculated because the average output voltage, it is 500 watts is the power, and the 500 watts is the power, and the load power supplied to 230 resistive load, the load writing is given as 230 volt. 230 volt is the writing of the resistive load, and power equal to 1 kW. From this specification, you can calculate what is the resistance value, which is equal to V squared by P, which is equal to 52.9 ohms. Therefore, the resistance is equal to 52.9 ohms. And for a full converter for a 500 watts output, the VDC, the required DC, or this is the resistance, and the required DC is given by VDC is given by square root of P into, or P equal to VD squared divided by RL, and here VDC required equal to square root of P into RL. Therefore, for 500 watts, root of 500 into whatever the resistance, which is equal to 162.6 volts. And for a full converter, the equation or the average voltage is given by 2 Vm by pi into cos alpha, or 2 into Vm equal to root of input voltage equal to 230. 2 into root 2 into 230 divided by pi into cos alpha. Or from this one, you can calculate what is the cos alpha, which is 0.785, or alpha equal to 32.28 degrees. Therefore, I naught equal to, that is, the load current is given by the average value of the DC voltage, which is equal to VDC equal to 162.6, that divided by the load resistance 52 point. For the load current is equal to 3.07 amperes, and the firing angle equal to 38.28 degrees. Now displacement power factor, in this case of a full converter, the displacement power factor equal to, that is cos phi 1, which is equal to cos alpha, or cos phi 1 equal to cos alpha means cos 38.28 or 0.785. For a full converter, the displacement power factor equal to 0.785. Continuing this one, for a full converter, if the current is continuous, a ripple free current is there in a full converter, the RMS value of the fundamental is equal to 2 root 2 I naught divided by pi. So for 2 into root 2 into load current is equal to 3.07. that divided by pi, 2.76 amperes. That is the RMS value of the fundamental. And the RMS value of the total source current is given by, which is equal to, in a full converter case, it is same as already we have derived this equation, which is equal to same as Is equal to I0, which is equal to 3.07. For we are calculating what is the RMS value of the fundamental and what is the total RMS value. The ratio of this one we call it as, it is equal to distortion factor. IS1 divided by IS, which is equal to 0.9. For the distortion factor is this one, and displacement power factor already calculated, which is equal to the point here, which is equal to 0.785. This is the cos alpha or cos phi 1 or cos alpha, 0.785, and distortion factor 0.9. Multiplication of the displacement power factor and distortion factor, which is equal to 0.707. That is the power factor. At the input side, the power factor equal to 0.707 for a fully controlled bridge circuit. And total harmonic distortion is given by square root of IS square minus IS1 square divided by IS1. IS1 is the fundamental RMS value. This is the total RMS value. And substituting here, we can see same thing here, 3.07 square minus 2.76 square under square root divided by 2.76 equal to 0.48, or 48% is the total harmonic distortion. Now another method to calculate, one more method is that to calculate the input power factor. This is the one method, multiplication of the distortion factor and displacement. Another method is that if you are assuming that all the component, I mean, of course all are ideal case, therefore input power will be equal to the output power. Therefore Vs into Is into cos phi equal to VDC into I0. That is another method here. For assuming the power loss in the components are 0, then RMS value of the source current equal to Is equal to I0. Already we know that Is equal to I0. Now from this equation, the power factor cos phi equal to here VDC divided by V, because Is and I0 will be cancelling. Therefore VDC divided by V, of course VDC divided by Vs, or here 162.6 is the average DC voltage divided by the RMS value of the input voltage 230, which is equal to 0.707. Same as we have seen here. This is one method. Otherwise, you can multiply the displacement power factor and distortion factor. Two methods are there. For in both cases, you will be getting the power factor here is equal to 0.707. Now continuing for a semi-converter circuit. Semi-converter circuit, already we are derived equations like, of course, first the load resistance is same. For 230 volt already we calculated 52.9 ohms. And for a 500 watts, the VDC equal to root of P into CR, we will be calculating the VDC required equal to 162.6. This also we already calculated. But the equation is different. The VDC equal to Vm by pi into 1 plus cos alpha. Using this equation, you can find out, from this equation, you can find out what is the cos alpha, 0.57. From this one, you can find out what is the firing angle required, 55.25 degrees. Then again, the load current is given by the DC voltage is equal to again 162.6. That divided by the load voltage, same as 3.07 is the load current for a even semi-converter circuit. This is the firing angle required. Therefore, the displacement power factor is given by cos fundamental phase angle shift, or cos phi 1, which is equal to cos minus alpha by 2. Previously, it was cos alpha by 2 for a fully controlled, but for a semi-converter, it is equal to cos minus alpha by 2, or it is equal to cos alpha by 2. Alpha is equal to 52.25. From that one, you can calculate the displacement power factor is now 0.886. Again, for a semi-converter circuit, we have derived the equation for what is the RMS value of the source current, which is equal to I0 into root of pi minus alpha divided by pi. Alpha already we calculated. Then substituting in this one, we will be getting it is equal to I0 equal to 3.07, V0 divided by RL, or sorry, VDC divided by RL, 3.07 amperes actually. Therefore, substituting this value of the load current I0 here, and in this equation you will be getting 2.56 amperes is the RMS value of the source current in a semi-converter case. 2.56 amperes. Then RMS value of the fundamental source current, that also derived previous slides, 2 root 2 I0 divided by pi into cos alpha by 2. Substituting that one, we will get 2.45 amperes. Therefore, this is the RMS value of the fundamental source current, and this is the RMS value of the total RMS value of 2.56 amperes. Now the ratio of the IS1 divided by IS1 divided by IS, that is called the distortion factor, 2.45 divided by 2.56, which is equal to 0.957. For distortion factor is this one, and already the displacement power factor equal to cosine of the cos phi 1, which is equal to cos alpha by 2. We already calculated, which is equal to 0.886. That is displacement power factor. And that distortion factor equal to 0.957. dpf into df, that is equal to total power factor, which is equal to 0.848. For a semi-converter circuit, in this case, it is equal to 0.848. So power factor. And total harmonic distortion is the same equation, root of is square minus is1 square divided by is, or root of, it is the numerator is the RMS value of the harmonics, and this is the RMS value of the fundamental. Related to fundamental, how much is the harmonics? Root of 2.56 square minus 2.45 square divided by 2.45, it is equal to 0.303, or 30.3% is the total harmonic distortion in the case of a semi-converter circuit.